The decline of eelgrass over the last 70 years has contributed to a major loss in critical habitat for marine life throughout the Peconic Estuary. Without eelgrass, finfish and shellfish populations suffer, and natural buffering for strong storm energy becomes diminished. The loss of eelgrass not only impacts ecosystems in our estuary, but also our fisheries and recreational economies that depend on this resource. Eelgrass beds were drastically reduced in the early 1930s due to a wasting disease caused by a slime mold, and further reduced in the 1980s and 1990s due to a harmful algal bloom, brown tide, which reduced the amount of sunlight that could reach our eelgrass habitats. Eelgrass is found in shallow, near-shore waters and requires good water quality and high light penetration to thrive. While wasting disease and brown tide blooms are not a significant problem in the Peconic Estuary today, other harmful algal blooms are present in the estuary, making it difficult for sunlight penetration. Boating and fishing activities, alterations to the shoreline, increasing water temperature, and water pollution also harm this important habitat. The Peconic Estuary program is contracting with the Research Foundation of SUNY Stony Brook to develop a seagrass bio-optical model that will provide information on what areas throughout the Peconic Estuary provide suitable habitat for eelgrass. This tool will guide future eelgrass protection and restoration projects as we gain a better understanding of light and temperature requirements for eelgrass in the Peconic Estuary. This is the critical next step towards the understanding of threats to the eelgrass community and where restoration projects have the best probability of success.
So this whole project came together when Chris Pickrell from Cornell and I were trying to wrestle with what is really driving the lack of recovery from seagrass in the Peconic. Our estuaries are all very different, and the Peconic is unique because it appears that there's plenty of light reaching the bottom, and yet grass isn't growing in places where we would expect it to grow. And so from those conversations came this idea of understanding what's controlling the light. In 2012, there was a Seagrass experts meeting where we brought people from around the country to come here and kind of look at our estuaries and what's going on. And one of the things that came out of that meeting was the experts suggested that we get a handle on what we call a bio-optical model, something that will help us understand what's changing the optical properties or limiting the light to the bottom. And so this project really came directly from that experts meeting.
So my name is Caitlin O'Toole, and I'm working with Stony Brook University. I'm a master's student here in Brad Peterson's lab. I was given a grant to work on water quality around the Peconic Estuary program, trying to figure out a restoration model for eelgrass around here. So my goal with the project is to kind of figure out ideal areas of where we could plant eelgrass, because you don't want to put all this time and effort and money into an area that is not an ideal place for seagrass. And so you want to take into account wind, because wind can rip up the seagrass. You want to take into account temperature, because if the eelgrass is light temperature stressed, it's not going to perform as well and could possibly die off. And as well as light, you want it to have enough light. So those are the main three metrics, and then you kind of want to make sure everything else is good in those places as well. So this is kind of going to give a more broad-based area of where we should be doing restoration, and then it'll allow for more higher resolution sampling to figure out the best places for this restoration. So my method of trying to figure that out is I put temperature loggers out that record temperature every 15 minutes in about 15 different locations throughout Peconic Bay. As many people know, we have a climate change issue, and so the waters are warming, and I'm trying to figure out if water temperature is has to do with why the eelgrass is dying off. However, in other bays, we're still seeing that the eelgrass is surviving, so we think that it might be a combination of the light and the temperature. Every 2 weeks, I went out and took water quality metrics, so I would go out and I would take chlorophyll measurements, total suspended solids, colored dissolved organic matter. I would take temperature, dissolved oxygen, salinity, and let's see, what else did I do? Oh, and I would take light measurements to figure out how much light was reaching the bottom of the water column. So basically what I was trying to do was take those light measurements, so the actual light measurements in the water, and create a model from the collected chlorophyll, total suspended solids, and color dissolved organic matter, and put them together in a way that if you take concentrations of those chlorophyll, TSS, and sedum, you get how much light is reaching the bottom. So you don't have to take this instrument out and figure out how much light is reaching the bottom with the instrument. You could do it just based off of what most people are collecting in their water quality programs.
Understanding a system is very complicated. There's lots of moving parts, and you have to kind of try to prioritize understanding what particular things are going on. And this was a project where we could understand an element of it. And so understanding light movement through water is not that complicated if you understand three basic elements. So the things that are limiting the water transparency are pretty much summed up in the dead particles, which we call total suspended solids, the living particles, which we measure as chlorophyll, and then the color, or what we call CDOM, or color dissolved organic matter. And if we have a handle on all three of those, then we can pretty much predict what light is going to reach to what level in the bottom. And then one of the elements of this project that I was most excited about was having a tool that we could then use to monitor what our management strategies impact they're having on changing light levels. And so the idea of this project was that we can develop a tool that hopefully will be living on. This is being put up on the web for the Peconic Estuary program, and the idea is that now that the hard work of creating the model is done, in 3, 4, 5 years, you could kind of go out and measure the properties again and say, well, how have they changed? How has our strategies to remove nitrogen, how has it affected the chlorophyll? And then thereby, how has it really changed the light levels reaching the bottom in the Peconic? And so I was most excited about kind of the applied nature of this model and how it could have an impact going on. Having this tool allows us to try to play different kind of management scenarios. Restoration is costly, and so we want to make sure that we're putting the dollars to the right places, and this is just a tool that can be used to kind of make sure that we're putting the limited resources that we have into the most appropriate places in the Peconic Estuary.
Models like the Seagrass bio-optical model can guide decision-making in preservation and restoration projects, creating a healthier Peconic Estuary for tomorrow and generations to come.